Imagine the strongest wind you have ever felt. Now imagine winds moving almost 5 times faster. That is the scale of the difference between Earth's extreme winds and the winds of Neptune. Earth can produce hurricanes, jet streams, and violent tornadoes, but Neptune operates on another level. On Neptune, atmospheric currents can exceed 1,200 miles per hour, or about 2,000 kilometers per hour. And the strangest part is that Neptune receives far less sunlight than our warm, energetic planet.
So where does all that incredible wind energy come from on such a cold and distant world?
To answer that question, we first need to understand what creates wind here on Earth. Then we can travel billions of kilometers outward and see why Neptune breaks almost every expectation. This is Earth versus Neptune, a comparison of 2 completely different atmospheric machines. And by the end, Earth's most terrifying winds may suddenly seem surprisingly slow. Wind on Earth begins with one basic ingredient: uneven heating from the sun. The equator receives more concentrated solar energy than regions near the poles. Warm air expands and rises, while cooler, denser air moves in to replace it. Those pressure differences begin moving enormous masses of air across the planet.
But Earth's rotation prevents that air from simply traveling in straight lines.
The Coriolis effect bends large-scale atmospheric motion as Earth turns beneath it. The result is a complex network of trade winds, westerlies, storms, and high-altitude jets. Near the ground, mountains, forests, cities, and oceans also influence how winds behave. Friction with Earth's surface generally slows the lowest part of the atmosphere. Climb higher, however, and that friction becomes much less important.
Near the tropopause, narrow rivers of fast-moving air form the powerful jet streams. Typical jet stream winds can travel around 110 miles per hour.
Under extreme temperature contrasts, those winds can reach 250 miles per hour or more. That is already faster than many high-performance cars can travel on the ground.
But the atmosphere can concentrate energy even more dramatically inside powerful storms.
Tropical cyclones convert heat from warm ocean water into organized atmospheric motion.
As pressure falls near the center, surrounding air accelerates inward and begins rotating.
The most intense hurricanes sustain winds exceeding 157 miles per hour. Individual gusts can become even faster when turbulence briefly concentrates the moving air.
Earth's official non-tornadic gust record reached 253 miles per hour in Australia. That extraordinary measurement occurred during tropical cyclone Olivia in April of 1996.
Tornadoes introduce another complication because their fastest winds are extremely difficult to measure directly.
Mobile Doppler radar can estimate extreme velocities without placing instruments directly inside the vortex.
Some tornado estimates can exceed the conventional wind records measured by weather stations.
So comparing planetary wind speeds requires us to compare measurements carefully, not just dramatic headlines.
For a clean benchmark, roughly 400 kilometers per hour represents Earth's strongest directly measured non-tornadic gust.
That sounds enormous, because for humans at ground level, it absolutely is. Yet against Neptune's fastest atmospheric currents, even that record is dramatically outmatched. To understand why, we must leave Earth's rocky surface completely behind. Our destination is the 8th major planet from the Sun, Neptune. Neptune orbits more than 30 times farther from the Sun than Earth does. At that distance, sunlight is roughly 900 times weaker than the sunlight reaching Earth. You might expect such a dark, cold planet to have a relatively quiet atmosphere. Instead, Neptune has the fastest known planetary winds in our solar system. Its upper atmosphere consists mainly of hydrogen and helium, with a smaller amount of methane. Methane absorbs red wavelengths of light and contributes to Neptune's characteristic blue appearance. Bright clouds high in the atmosphere can contain frozen methane crystals. But unlike Earth, Neptune gives us no solid ground beneath those clouds.
Its atmosphere gradually becomes deeper, denser material surrounding the planet's mysterious interior.
That difference alone fundamentally changes the way atmospheric circulation can behave. Earth's lower winds continually interact with continents, mountains, trees, waves, and countless surface obstacles. Neptune has no comparable rocky landscape dragging directly against its visible cloud-level winds.
But low friction alone cannot explain winds approaching 2,000 kilometers per hour.
Another piece of the puzzle lies deep inside the planet itself.
Neptune releases substantial internal heat into an atmosphere, receiving very little solar energy.
This internal energy helps drive convection, transporting heat upward through different atmospheric layers. Rising and sinking material can feed large-scale circulation far above the planet's interior.
Neptune also rotates surprisingly quickly, completing one day in roughly 16 hours.
Rapid rotation strongly influences atmospheric motion through the same basic rotational physics affecting Earth.
But the final wind pattern is very different from anything familiar in Earth's weather. At some latitudes, Neptune's atmosphere races westward relative to the planet's interior rotation. At others, atmospheric motion changes speed and direction, producing enormous bands of planetary circulation. Those differences in velocity create wind shear, an important ingredient in Neptune's turbulent weather. Large storms can appear as dark vortices surrounded by bright, rapidly changing clouds. Voyager 2 famously observed the Great Dark Spot during its 1989 Neptune flyby. That enormous storm was once large enough for an entire Earth to fit inside its outline. But unlike permanent surface features, Neptune's dark storms can form, evolve, and disappear.
Later observations have revealed other dark vortices appearing at different locations across the planet.
This tells scientists that Neptune's atmosphere remains extraordinarily active over time. And those storms are embedded inside an even larger system of powerful global winds. Near some regions, measured winds approach roughly 1,200 miles per hour. That is close to 2,000 kilometers per hour, moving through a hydrogen-rich atmosphere. At that speed, an atmospheric feature could cross the continental United States in only a few hours. The number becomes even more remarkable when placed directly beside Earth's wind records. Now we can finally make the comparison on equal terms. Earth's record non-tornadic gust, about 408 kilometers per hour. Neptune's fastest observed atmospheric winds, roughly 2,000 kilometers per hour. By speed alone, Neptune's extreme winds are almost 5 times faster than that Earth record. Compare Neptune with an ordinary 100-kilometer-per-hour storm, and the difference becomes 20-fold. Against average jet stream speeds, Neptune still wins by an enormous margin. But speed does not automatically tell us how the wind would actually feel.
The force produced by moving gas also depends strongly on its density. A fast flow of thin gas is not identical to the same speed in dense air.
Pressure also changes dramatically as you move deeper into Neptune's atmosphere. So there is no single Neptune surface where we can place an anemometer like on Earth. Instead, scientists track moving cloud features and atmospheric patterns to estimate wind velocities. Voyager 2 provided the first detailed close-up measurements during its historic flyby.
Hubble later allowed astronomers to monitor Neptune's changing atmosphere across many years.
And the James Webb Space Telescope has revealed high clouds and atmospheric structure in infrared light. Together, these observations show a planet whose atmosphere is anything but frozen and quiet. Earth and Neptune therefore generate winds from very different combinations of energy and structure. Earth's atmosphere is powered primarily by sunlight, interacting with oceans, land, water, and rotation. Neptune receives weak sunlight, but supplements it with energy escaping from its interior. Earth has a solid surface that introduces friction and strongly shapes the lower atmosphere. Neptune's visible atmosphere floats above thousands of kilometers of deeper fluid and gas. Earth completes a rotation in about 24 hours. Neptune rotates in roughly 16. Those differences help produce atmospheric circulation patterns that are dramatically unlike one another. Yet both worlds obey the same fundamental physics of pressure, temperature, rotation, and fluid motion. That is what makes Neptune so useful for understanding planetary atmospheres beyond Earth.
It shows how radically weather can change when familiar physical ingredients are rearranged.
Imagine trying to design a probe capable of exploring those rapidly moving cloud layers. Engineers would need to account for extreme winds, pressure changes, temperature, and communication distance. And unlike a Mars lander, there would be no solid Neptune surface waiting below. Eventually, increasing pressure and temperature would create conditions completely different from Earth's atmosphere. That makes direct exploration extraordinarily challenging, leaving remote observations crucial for understanding its weather.
Models must explain how internal heat, rotation, convection, and atmospheric waves interact together. Every new observation gives researchers another piece of this gigantic atmospheric puzzle. And the comparison with Earth reminds us that our own atmosphere represents only one possible outcome. Across the solar system, weather can operate at scales far beyond everyday human experience. So which planet wins our wind speed comparison? On raw atmospheric velocity, there is no contest. Earth can produce extraordinarily violent winds, especially inside its most powerful storms.
Its strongest directly measured non-tornadic gust reached more than 400 kilometers per hour.
High-altitude jet streams can also reach similar speeds when atmospheric temperature contrasts become extreme. But Neptune pushes atmospheric motion toward roughly 2,000 kilometers per hour. That makes the distant blue ice giant the undisputed wind speed champion among our solar system's planets.
And surprisingly, this champion circles the sun, where daylight is hundreds of times weaker than on Earth. Its winds are a reminder that planetary weather depends on much more than sunlight alone. Internal heat, rotation, atmospheric composition, depth, and fluid dynamics can transform an entire world's weather. Earth has incredible winds. But when speed is the question, Neptune lives in an entirely different league.